Let's have a quick overview on the different experimental setups that consist the charge to mass ratio of an electron experiment. First off, over here we have two circular coils. These two circular coils, they are identical, meaning that they both have the same number of turns, 154 number of turns, and they both have the same diameter. Moreover, they are disposed in such a way to be facing each other. So in a sense, they are parallel to each other. Therefore, when you have an electrical current applied to these two coils, in that case you have a magnetic field that is going to be generated by them. But moreover, since we have identical circular coils, therefore that magnetic field is going to be a uniform magnetic field, and it's going to be concentrated in its majority at the center. So over here at the central region between these two coils, we are going to have a uniform magnetic field. So when we say uniform magnetic field, we actually mean that over here we have, in a sense, parallel magnetic field lines. So the magnetic field lines, they are going to be horizontal at the center. They are uniform, so they are horizontal and they are parallel to each other right at the central region between these two coils. And like I said, the majority of the magnetic field is going to be concentrated at the center. However, when you move toward the edge of each coil, that uniformity of the magnetic field is going somehow to drop down. Then at the central region, over here we have the evacuated bulb. So that evacuated bulb is going to be located right at the center between these two coils, where we have the presence of a uniform magnetic field. So in that case, if each circular coil has a certain radius r, therefore that bulb is going to be located right at a distance of r over 2 from each coil. So it's going to be located at half radius from each coil. And like I said before, that bulb over here is going to contain a small amount of mercury gas in order to render the trajectory of the electrons visible within that bulb. Now if you have a look over here to one side of that bulb, we can see that we have a device which is none other but the electron gun device, which we have talked about it before. So the electron gun, like we said, it consists of two metal plates, of a cathode that is connected to the negative terminal of a power source, and an anode which is connected to the positive terminal of a power source. Moreover, the cathode is going to be equipped with a heater. So in that case, when the cathode plate becomes heated enough, it's going to generate a stream of electrons. However, in order for these electrons to be transmitted toward the anode, and therefore in order for them to enter the bulb region, they must be supplied with an accelerating voltage between the cathode and the anode. Now if we look over here at the apex, if we have a look at the apex of that electron gun, we can clearly see that the apex is actually equipped with a very small hole. It is actually being pierced right at the apex. Therefore that small hole is going to allow for a fraction of that beam of electrons to pass through it and therefore to enter into that bulb region. If we have a look over here, we have two different function generators. So what would be the role of each power source? Starting with the power source on the left side. The power source on the left side is going to be connected to these two Helmholtz coils in order to supply them with an electrical current, and therefore in order to generate a magnetic field right at the central region. So by using that power source, we are going to actually to be manipulating the amount of the current that is being supplied to these two coils, and therefore we are going to be manipulating with the strength of the magnetic field that is being generated by them. And over here we have an ammeter which is connected in series to these two coils and to that power source in order to read the amount of the electrical current that we are applying to these two coils over here. So in a sense, whenever we are varying with the amount of the electrical current applied, therefore you are varying with the intensity or with the strength of that magnetic field, and as well you are varying actually with the strength of the magnetic force that is going to be exerted by that magnetic field on the electron beam, as we are going to see in a bit. Now over here we have the second function generator. So what would be the role of the second function generator? We said before that electron gun over here, once you have the cathode plate heated enough, it's going to generate a stream of electrons. However, for that stream of electron, in order for it to enter into the bulb region, it must be supplied with an accelerating voltage between the cathode and the anode. So that function generator over here, its role is going to be to apply a potential difference between the cathode and the anode in order to supply the electrons with an accelerating voltage, or in a sense, in order to supply them with a kinetic energy for them to be transmitted into that bulb region. So as we can see over here, we have these connections coming out of that function generator and being connected from one side to the tube of that electron gun. So that tube over here is internally connected to that electron gun. And then over here we have a voltmeter, which is going to be connected in parallel with that tube in order to read the amount of the accelerating voltage that we are applying between the cathode and the anode. So one function generator is going to be connected to these two coils in order to supply them with a separate electrical current in order to generate a magnetic field. And that second function generator over here, its role is going to be to supply the electrons that are generated by the cathode plate with an accelerating voltage for them actually to be transmitted or to be emitted into that bulb region. So we had to dim the lights in order to render the trajectory of the electrons visible within that bulb. So as we can see over here, we have basically a circular trajectory for the electron beam, which is colored in orange. And the orange in that case is an indication of the light that is being given off after collisions happen between the electrons and between the mercury atom. So as we have said before, that evacuated bulb, it contains a small amount of mercury gas. So upon the entrance of the electrons into that bulb, they are going to collide with the atoms of mercury. And therefore, upon collision, a transfer of energy is going to happen from the electrons toward these mercury atoms, which they are going to be excited, and then they are going to be de-excited to a lower energy state, and in the process they are going to emit a certain characteristic light, a certain photon of light. And that photon of light over here is emitted in the form of an orange light. So as we can see, we have a circular orange path for the electron beams. Now, what we need to do in that case is we need to be manipulating from one side with the amount of the accelerating voltage applied, and from the other side we are going to be manipulating with the strength of the magnetic field from one side, and therefore with the strength of the magnetic force that is going to be acting on these electrons. So what would happen in that case if there is no magnetic field in that central region between these two coils? So let's say that we are going to turn off the power source which is connected to these two circular coils. So as we can see in that case, we don't have any longer a circular path for the electrons, but rather we have over here a straight line for the trajectory of the electrons, meaning that the electrons now, they are being shot vertically upward, and they are not under the effect of any magnetic field, and therefore they are not under the effect of any magnetic force acting on them and forcing them to move along a circular path. So in the absence of a magnetic field, as we can see, the electrons are going to be moving vertically upward. There is no magnetic field region, and therefore there is no magnetic force acting on them. Therefore, the moment we turn on the power source again, now we have an electrical current flowing through these two coils, and therefore we are going to have a magnetic field region, and as a result we are going to have a magnetic force acting on these moving charges, on these moving electrons, and therefore now the electrons, they are forced to move along a circular path. Now what would happen if we actually manipulate with the intensity of the electrical current that is being applied to these two circular coils? So we know that a magnetic field is generated by the electrical current. Therefore, the magnetic field and the electrical current, they are directly proportional to each other, or the strength of the magnetic field is directly proportional to the amount of the current applied. And therefore, the magnetic force is also going to be proportional to the strength of the magnetic field. So when you increase the electrical current, therefore you are incrementing the strength of the magnetic field, and as a result you are also incrementing the strength of the magnetic force. So in that case, if we increase over here the amount of the electrical current applied, as we can see now, the electron beam, or the circular motion of the electron beam, it became narrower. So that's an indication of what? We have seen before that the magnetic force acting on these moving charges is a centripetal force, which is directed toward the center. So the magnetic force is a centripetal force directed toward the center. So when you increment the amount of the intensity of the electrical current, therefore you are not only incrementing the amount of the magnetic field, but also incrementing the amount of the magnetic force. So now the magnetic force is going to be pulling much stronger toward the center of curvature of that circular path. So that implies now the magnetic force is forcing the electrons to move along a smaller radius, along a smaller orbit. So whenever you increment the electrical current, therefore you are incrementing the amount of the magnetic force applied. And as a result of that, as you can see over here, now you are forcing actually the electron to move along a smaller orbit, a smaller radius of orbit. If we have a look at that lab report over here, we can clearly see that we have three different voltages, V1 of 100 volts, V2 of 120, and V3 of 140. So each voltage in that case is going to correspond to the amount of the accelerating voltage that is being applied between the cathode and the anode in order to accelerate the electrons into the bulb region. Let's say we start with V1 at 100 volts. So we are starting with an accelerating voltage between the cathode and the anode of 100 volts. However, over here you have different radii of curvature or different radii of orbits. So these radii over here, they correspond to the radius of orbit of the electron beam, which is undergoing a circular motion. So for the first trial, they want you actually, they want for the electron beam to undergo a circular motion at a certain radius of orbit of 0.02 meters. For the second trial, they want for the electron beam to undergo a certain circular motion at a radius of orbit of 0.03. For the third trial, they want for that electron beam to undergo a circular motion at a radius of orbit of 0.04 meters. And for the fourth trial, they want for that electron beam to be moving along a circular path at a radius of orbit of 0.05 meters. But how can we indicate precisely these radii of orbit within that bulb region? If we have a look over here, we can clearly see that within that bulb, we have something that resembles a ladder. And that ladder is actually placed horizontally, as we can see. So that ladder, it consists of different parts, which we are going to call them a rung. So each part is going to be called a rung. However, each part over here is going to correspond to a certain diameter. So for example, for that first rung, the diameter of that first rung is going to be the double of 0.04 meters. So over here, the radius, which is none other but the distance from the apex of that electron gun toward the middle, is going to be none other but a radius of 0.04 meters. Then if we move on to that second rung, therefore the middle distance between that rung and between the apex of the electron gun is going to be none other but 0.03 meters. And then over here we have the third part of that bridge or of that ladder, which is going to be located at a distance which is none other but the double of the radius of 0.04 meters. And finally we have that fourth rung of that bridge, which is going to be located at a distance of 2 times 0.05 meters from the apex of that electron gun. So in that case, what we need to do is the following. We need to be adjusting the circular path of the electron beam in order to be tangential to each one of these rungs, to each one of these parts of that ladder. So for example, if the electron beam, let's say it's being tangential to that first part over here, therefore that electron beam is going to be moving along a circular path at a certain radius of orbit of 0.02 meters. Now if we adjust the electron beam to be tangential to that second part, therefore the electron beam is going to be moving along a circular path which has a radius of orbit of 0.03, and the same thing for the third part and the fourth part. So each time we need to be adjusting the electron beam in order to be tangential to each one of these parts of that ladder over here. So as we have seen before, in order to adjust the electron beam, all we have to do is actually adjusting the amount of the electrical current that is being applied to these two circular coils, because as we have seen, the intensity is directly related to the strength of the magnetic field, and the strength of the magnetic field is directly related to the strength of the magnetic force acting on these moving electrons. Therefore, whenever you increment the intensity, you are actually incrementing the magnetic force, and therefore the circular beam either becomes narrower or it becomes greater whenever you increase or you decrease the amount of the intensity of the electrical current applied. So first off, over here we are going to be manipulating with the amount of the accelerating voltage applied. We are going to reduce that accelerating voltage to 100 volts. Since for the first trial we are going to be operating at a certain accelerating voltage at 100 volts. So over here we have adjusted the accelerating voltage to 100.7 volts, almost 100 volts. Now over here, if we have a look over here, we can clearly see that the path of the electrons within that bulb is not actually a circular path, but rather it's a helix, which is an indication that the electrons in that case, they are not being shot upwardly at an angle of 90 degrees or they are not making an angle of 90 degrees with the magnetic field that is being generated by these two circular coils. So whenever the angle is not 90 degrees between the trajectory of the electrons and between the direction of the magnetic field, therefore we are going to obtain a helix and not a circular path for the electrons. So what we need to do is, we need actually to rotate the tube of that bulb in order to adjust the direction of the electrons to become perpendicular to the direction of the magnetic field. So now, as we can see, we have a perfectly circular shape for the trajectory of the electron beam within that bulb. However, as we can see over here, the electron beam is not actually tangential to that first rung, but rather it exceeds it a little bit. And we need to adjust the trajectory of the electron beam to be tangential to that first rung. So what we are going to do is, we are going to be manipulating with the amount of the electrical current that is being applied to these two circular coils in order to render the trajectory of that electron beam tangential to that first rung. So as we can see now, we have the electron beam being tangential to that first rung. So after making that electron beam, that circular electron beam tangential to that first rung, what we need to do next is we need to record the corresponding amount of the electrical current that we have applied to these two circular coils in order to adjust the trajectory of that electron beam to become tangential at that first rung. So over here, using that ammeter, you are going to be recording the corresponding amount of current that you have applied for the first trial, which is 1.25 amps. So in that table over here, you are going to start by recording the first amount of the intensity, or the first value for the electrical current, which is going to be 1.25 amps. Now moving on to the second radius of curvature, 0.03. So now what we need to do is actually we need to adjust the amount of the electrical current applied in order to make that circular beam tangential to that second rung. So now, as we can see, we have the electron beam being tangential, almost, it's not yet tangential. We need to adjust the amount of the electrical current again. All right. So now we have adjusted the intensity of the electrical current, and therefore we have adjusted the strength of that magnetic force acting on these electrons in order to render that electron beam tangential to that second rung. And then you record the second value for the electrical current. So as we can see now, the value of the electrical current, it actually dropped, which is logical. It dropped from 1.25 to 0.28, because whenever you want actually to render the radius of orbit bigger, therefore you have to decrease the amount of the magnetic force which is acting on these electrons. And to decrease the amount of that magnetic force, you have actually to decrease the amount of the electrical current applied. So for that second trial over here, you are going to record the value of 0.28 amps. And then the same thing for 0.04 and 0.05 radii of orbit. Now in the second part, what you are going to do is actually, all over again, over here you are going to be incrementing now the accelerating voltage to 120 volts. And in a similar manner, you are going to be adjusting the direction of that electron beam in order to render it tangential to the first rung, the second rung, the third and the fourth. And for each trial you are going also to be recording the corresponding value for the electrical current. And then the same thing for the last part, at which you are going to be operating at a certain accelerating voltage of 140 volts. So let's have one more trial at second accelerating voltage of 120 volts. So like I said, you are going to be manipulating with the amount of the electrical current applied in order to render the trajectory of the electron beam tangential to that first rung. So in order to do so, you are going actually to be incrementing the amount of the electrical current applied in order to increment the amount of the magnetic force acting on these moving electrons, and therefore you are rendering the circular beam much more narrower. And therefore we have the circular beam being tangential to that first rung. And then you go on and you record the corresponding value for the electrical current, which is now at 2.68 amps. So as we can see now, we have an increment regarding the amount of the electrical current applied, since we have actually incremented in that case the accelerating voltage. So when you incremented the accelerating voltage, you have basically incremented the speed at which the electron beam is entering into that bulb region. Therefore you are going to need now a much bigger force acting on them in order to render that trajectory narrower, and therefore in order for them to be tangential at that first rung. So for that first value over here, now we have a value for the electrical current of 2.68 amps. And the same thing for the second, the third, and the fourth trial. Let's have a look at the report that you are going to be solving. So for the first accelerating voltage, let's say of V1 equal to 100 volts, you have the following table, which consists of the different radii of orbits, 0.02, 0.03, 0.04, and 0.05. And then over here you have the amount of the intensity applied, the amount of the electrical current applied. Then you have the inverse of the radius squared. Then over here you have the magnetic field, and you have the magnetic field squared. So as we have seen before, the electrical current in that case is going to be adjusted in order to render the trajectory of the electron beam tangential to each rung, and therefore in order for the electron beam to be moving along a certain radius of curvature. So over here we have certain values for I1, I2, I3, and I4. And over here you simply take the square of each radius and then you take its inverse and you find the values. Now regarding the magnetic field, that magnetic field is going to be the strength of the magnetic field that is being generated by these two circular coils. So in order to find the value for each magnetic field, you are going to go back to that equation over here, which is an equation that is specific for a Helmholtz coils, for a combination of two circular coils disposed in a way to be parallel to each other. So that equation, it was basically determined from the equation that we have established previously for a circular coil, for a single circular coil. So in the previous experiment, we have established that expression, which was specific for a circular coil. However, that expression, it was now adjusted in order to be applicable to a set of Helmholtz coils. First off, for a Helmholtz coil, you have to adjust for the fact that the bulb is situated at a certain distance of R/2 from each coil. So over here in that expression, we are replacing X by R/2. And then we are accounting for the fact that instead of having one circular coil, so that expression over here is for one circular coil, we have now two circular coils. Therefore, you are going to be multiplying that expression by 2. Therefore, after you do the necessary simplifications, you are going to find out that the expression for the magnetic field is given by the following equation, which is 4/5 to power 3/2 multiplied by mu0 times the number of turns times the electrical current over R. Now, N over here would be the number of turns of each circular coil. So over here, you replace N by 154. However, regarding that radius R, now R is not these radii of orbits over here. It's not the radius of orbit of the electron beam which is undergoing a circular motion, but rather R over here is going to be the radius of each circular coil. So R is going to be equal to 0.2 meters. So you have not to confuse between R, which is the radius of the circular coil, and the other radii of orbits, which are the radii of orbit of the electron beam, which is undergoing a circular motion. And then over here you have I, which is going to be the amount of current in each trial. So for trial number 1, let's say, so for the first trial, you are going to be finding B1. B1, which is going to be equal in that case 4/5 to power 3/2 multiplied by mu0 times the number of turns, which is 154, times the first value of the electrical current I1. So over here you plug in the value of I1, the first value of the electrical current, divided by the radius, which is 0.2 meters. The same thing for the second trial, B2, 4/5 to power 3/2 multiplied by mu0 times 154, now times the second value of the electrical current divided by the radius of that circular coil, which is 0.2, the same thing for B3 and B4. So after finding all the values for the magnetic field, now we are going to be squaring each value over here in order to find B squared. And then you have to repeat the same thing all over again for the second accelerating voltage and for the third accelerating voltage. The first question in that lab report, they ask you to use linear regression in order to find the slope of 1/r squared versus v squared. So over here they are asking you actually to find the slope of 1/r squared versus v squared. So basically, over here 1/r squared is going to be the y variable, and v squared over here is going to be the x variable. So you have the slope of y versus x. We want to find the slope of y versus x, where y would be 1 over the radius of orbit squared versus the magnetic field squared. After you find the slope of 1/r squared versus v squared, of course you are going to find the error. Then they are asking you to deduce an expression for the slope of 1 over r squared versus v squared. So how can we determine an expression for the slope in that case? If we go back to that equation which we have established previously, that E over m is equal to 2v over b squared times r squared. So if we go back to that expression, which relates the charge to mass ratio of an electron, which is equal to 2 times the voltage over b squared times r squared, we are going to adjust that equation in order to become of the form y equal ax, where y in that case would be 1 over r squared and x would be b squared. So that equation would be adjusted in the following form to become 1 over r squared is equal to E over m times b squared times 1 over 2v. So we can write it in the following form: 1 over r squared equal to E over m times 1 over 2v times b squared, where 1 over r squared would be the y and b squared would be the x variable. Therefore, the term that you have left over here, which is multiplied by x, is going to be the expression of slope. So after you find the expression of slope, now they ask you to deduce or to determine the experimental value for the charge to mass ratio. So you have to deduce the experimental value of E over m. So having the slope equal to that, therefore you can find an expression for E over m, which is going to be expressed in terms of the accelerating voltage and the terms of slope, and then you can find an experimental value for E over m. However, after you find that experimental value, and now they ask you to find over here the error on E over m. How can you find the error in that case? So to find the error is going to be none other but the propagation of error method. So first off, since the voltage, it was measured using a voltmeter, therefore you are going to have a certain error associated with the accelerating voltage. And the error in that case is going to be the least subdivision that you can read on that voltmeter. So for example, let's say you were reading a value of 100.7 volts. Therefore, the least subdivision that you can read on that voltmeter is going to be alpha equal to 0.1 volts. That would be the error on the voltage. And then you have an error on slope, which was determined in the previous part. Therefore, E over m is going to be a function that depends on two variables. It depends on the voltage and it depends on slope. Therefore, to find the error on E over m, you are going to be applying the propagation of error, or you are going to be doing two partial derivatives. The first partial derivative of E over m with respect to the voltage, and the second partial derivative of E over m with respect to slope, and then you carry on, you fill in the values, and you find the error on E over m. That would be for the first trial. Then you have to repeat the same thing all over again for the second accelerating voltage of 120, and then for the third accelerating voltage of 140 volts. So in total you have 3 linear regressions to do, you have 3 propagations error to do, and therefore you are going to be finding 3 values for E over m, which logically they should be compatible, they should be the same. Because like we said before, E over m is a constant for any accelerating voltage applied.